All right, so let's examine in greater detail some of the details we skipped over in Module 1 regarding the weak form derivation. So in order to get a flexible method, we have to be able to generate an arbitrary order solution approximation. So the question is, we certainly can make a higher order solution approximation manually, but we'd ideally like to be able to generate this with code so that we don't have to completely rewrite the routine if we'd like to move from, let's say, 6th order to 7th order. So when we talked about the construction of the bases for the solution approximation, we chose ramp functions and didn't really belabor the point any further. But we can talk about, in general, the solution approximation being some linear combination of some basis functions and some weighting coefficients on those basis functions. And we can take two different tacts with this. We can think of these points here, or these coefficients here, being nodal values, or we could think of them as being weights on modal values. So to clarify what I mean here, imagine that we have some particular exact analytical function that we'd like to interpolate. We could choose a set of points that we'd like to specifically have our interpolation or our approximation interpolate. And so our approximation would, if I was able to draw a little bit better, would be sure to interpolate at these points. So if we think about it then, each of these points, call them y sub I, gives us some idea of what's going on in our interpolation. So in that case, these would be these yi, and these basis functions would then have to somehow accommodate the support of each particular point. So you can imagine you'd probably have some sort of basis function for each of your interpolation points. So this is what's called a nodal approximation. We're seeking a approximation such that our interpolation satisfies at a particular set of nodes. We could instead take a modal approach. Now, a modal approach essentially tries to take your, again, let's say some sort of analytical solution, and it tries to break it down into a constituent set of modes. So you can think of modes being an increasingly higher order basis. So the lowest order mode would be a constant. The second highest mode would be linear. The next highest mode would be quadratic, and so on and so forth. And so some linear combination of each of these progressively higher modes would hopefully be able to recover your exact solution. So you can think of this as sort of a direct analog to a Fourier transform or something like that, where you're decomposing a signal into constituent lower order pieces. So in that case, then, the coefficients here don't have a direct physical significance in terms of the overall function that you seek to approximate. They're really just the weighting on the particular modal bases. So the larger it is, the larger the influence that modal basis would have on your reconstruction. So you can imagine then that if you had a analytical solution that you were able to represent very, very well with, let's say, 6 of the lowest modal basis functions, there likely is some non-zero coefficient for the higher order terms as well, if it's not a polynomial or something like that. But those values, the magnitude of those coefficients on those higher order modes is likely very, very small compared to the low order modes which dominate. So we could take either of these approaches to try to construct our higher order solution approximation. For the purposes of the rest of Module 3, we'll take a nodal approach. And either one has their advantages and disadvantages. One of the nice features of the nodal approximation is if you wanted to extend your high-order solver from 1D to 2D, there's a very slick way of doing so that essentially allows you to just have a number of 1D problems all tied together that give you your 2D phenomena, whereas expanding a modal approach to a two-dimensional or three-dimensional situation means you go from needing one-dimensional modes to now you could imagine some sort of mode surface that describes the deformation in a two-dimensional domain. And so those are a little bit more tricky to construct.